All right, welcome back. In this video, we'll be looking for, like I said in the last video, we'll be looking for necessary and sufficient condition for two spans to be equal. So I'm going to take two subset S and T of any vector space V. Then we'll first prove that if S is inside span of T, then span of S will also be inside span of T. All right, and finally, we'll prove that span of S and span of T are equal if and only if. So that means our condition are necessary and sufficient. They're equivalent. If the following two conditions hold. So I need S to be inside span of T, and I need T to be inside span of S. So it's symmetrical. All right, so before proving the theorem, I'm going to recall something about set theory. We used it. I had forgotten to write it then, so I'm writing it now. We used it in a proof right here. So to prove that two sets are equal, we showed that one was inside the other and vice versa. And so that's what I want to write down. I should have put it earlier. I'm sorry about that. So two sets are equal if and only if A is inside B and B is inside A. And so that means that if I want to show that two sets are equal, I could show that if A is in A, then A is in B. So every element of A is in B. And then if B is in B, then B is in A. And every element of B is in A. All right, so let's prove this theorem. I'm going to assume that S is inside span of T. I need to show that span of S is inside span of T. That's not hard because we've done most of the work before. So we've done most of the work in Theorem 1.3.1. So we proved that span of S is the smallest subspace containing S. But span of T, by the same theorem, is a subspace, and we're assuming it contains S. So by Theorem 1.3.1, span of T is a subspace. And so it's a subspace, and we're assuming that it contains S. So S is inside span of T, means that span of S is inside span of T. All right, that's it for part one. We're going to use part one and part two, which is why it's there. In part two, I want to prove an if and only if. And if you remember, I need to show that the two boxes are equivalent. So in the first part, I'm going to assume box one, and I'm going to prove box two. And then in the second part, I'm going to assume box two, and I'm going to prove box one. All right, so let's start. Assume that span of S is equal to span of T. So that's box one. I want to prove that S is inside span of S. Well, sorry, S is inside span of T, but by the theorem that we proved, so by Theorem 1.3.1, S is inside span of S, which is equal to span of T. And so S is inside span of T. Actually, oh, that's okay. And the same theorem, T is inside span of T, but span of T is span of S, and so S is inside span of T. Sorry, T is inside span of S. Sorry, I'm kidding. Too many similar letters. All right, so that proves one direction, proves that box 1 implies box 2. Now we're going to assume that S is inside span of T and T is inside span of S, and we want to show that span of S equals span of T. All right, let's do that. If S is inside span of T, then by first condition here that we proved over here, we'll get that span of S is inside span of T. So all the elements of span of S are inside span of T. But now we're going to apply it with S and T reversed. That's going to tell us that span of T is contained inside span of S. And then these two, all the elements of span of S are in span of T, and all the elements of span of T are span of S, so they have the same elements. And so they're equal. All right, that's all. So not very complicated. Frankly, most of the work we did in Theorem 1.3.1.